Okay, so if you can, please turn on your videos and let's continue from where we were last class. Okay, so we were looking at this problem, right? So we said x1 through x2k were independent Bernoulli P random variables. Okay, now what we want to do is like we define yk. This is the binomial random variable x1 through xk. Okay, and we also have y2k, which is x1 all the way through xk, plus you also add the remaining random variables. Okay, now we know that yk is binomial. It's a binomial random variable with parameters k and p, and this is a binomial random variable with parameters 2k and p. Okay, now these are all random variables defined in the same probability space. Okay, now the question we were asking last class is can we estimate y2k from yk? Okay, so how would we estimate y2k from yk? Okay, so there are two questions here. Like one is we know p, we know the parameter p, and the more realistic scenarios where we do not know p. Okay, so there are many variations that we can make from by playing around with this setup. Okay, so one very interesting answer was when we do not know p, a good estimate for y2k from yk is 2 times yk. Okay, when we know p, what would be a good estimate for yk? Sorry, y2k.
Are you asking for expectation?
No. Right now, we are just going by what I'm just asking you to guess right now. Okay, we'll formalize all of this. So, Stephanie, very good. So, NP would be the expected. So, Y2K has two components, right? So, this part is YK, and this part we do not see. Okay, so for the part we do not see, okay, the expected value of the part that we do not see, if we wanted to use one number to represent the part we do not see, that would be k times p. Okay, so what would be, can you, so that part is right, but knowing this, can you tell me what is the estimate of y2k from yk? Very good. Okay, so what Stephanie is saying is something like this. Okay, remember that y2k has two parts. Okay, we have seen the blue part. Okay, and we don't have information about the red part. Okay, so does that make sense to everyone? Sorry, does that make sense to everyone? Okay, so now what we are going to do is, like the part we have seen, we are going to use what we have seen. Okay, and the part that we haven't seen, the red part, y xk plus 1 through x2k, okay, we want to represent it with one number. Okay, and so we are going to use the expectation, and the expectation is k times p. Okay, the red part is the sum of k different k different Bernoulli p random variables, which we know. Okay, and the best way to represent a random variable with a number is using its expectation. Okay, and so that would be k times p. Okay, so is everyone okay with this? Okay, so two completely reasonable estimates. Okay, there are four different contexts, but there are two completely reasonable estimates. Okay, now, okay, so is everyone okay with this? Okay, so we are going to see like variations of both of these. Okay, we are going to see variations for both of these. We will say, for example, that we'll be able to interpret this 2 times yk in the same context as yk plus k times p. So we are going to see like various interpretations for both of this and also get new estimates. Okay, so and they all correspond to different ways about thinking about estimation. Okay, so when you do statistics, there are many different ways where you think about estimation, and each of them will find belongs to a different line of thinking. Okay, so what we also said last class was when we want to estimate, so suppose x and z are two random variables in the same probability space. Okay, then maybe we do y. I'll use z later. Okay, so then the best estimate of x using an observation of s. Okay, so we just mentioned this. Okay, so and we just kind of left it like this last class. Okay, and today we are going to understand what this estimate is. Okay, the setup is something like this. The setup is exactly what we have. You have some probability space. There are two different random variables x and y. Okay, you only get to see one of them. Okay, we get to see, in this case, we get to only see the green random variable. Okay, we do not see the red random variable. Why? Okay, but you want to estimate the red random variable. I'm sorry, like I don't know why this changed to me. Okay, you want to estimate the red random variable from what you have observed. Okay, so you don't get to see y, but you want to make your best guess about what the random variable y is, not its expectation, not a number. Okay, the exact value of this random variable. Okay, using your expectation of using your observation of x. Okay, this is something like here. Look at both these estimates. Okay, both of these estimates, they're not fixed numbers. They both rely on yk. Okay, and yk itself is random. Okay, yk could be any number from 0 to k. What this estimate would mean is if yk happens to be the number 3, our estimate will be 6. If yk happens to be the number 4, our estimate will be 8, and so on. Okay, so this is not a fixed number. Okay, so this is not a fixed number. Okay, this is a function of yk. Right, so different values of yk will give us different estimates. So different observations will give us different estimates of y2k. And that's natural, right? Because if we see a different value for yk, our estimate of y2k should also be different. Okay, so does this make sense? Okay, and this particular quantity that we write also behaves in the same way. Okay, it's not a fixed number. Okay, so expectation of y is a fixed number. Okay, but this particular quantity is also a function of x, right? So expectation of y given x, again, this we call it conditional expectation, and this is not a number, right? So this is not a number, it's a function of the random variable x. Okay, so it's not a function of y. Okay, so it's a function of the random variable x. Okay, so here, like, so that's why I'm highlighting this in green. Okay, this particular quantity, expectation of y given x, it is not a number. Okay, and there's a reason I'm repeating it so many times. Okay, it is actually a function of the random variable x. Okay, so is everyone so uh, so we are going to define what this quantity really is. Okay, so if, right, so to do so, we'll do this. Okay, so we are going to look at the event that capital X, the random variable capital X, takes on the value little x. Okay, now this is an event. Okay, now condition on this event, okay, this is the sum over all possible values y can take. Okay, and this is y times the conditional probability y equals little y given x. Okay, when we write a summation like this, okay, this little y is a dummy variable, right? We just sum over all possible values it can take in this set. Okay, so this is the set of values y can take. Right, so if y is binomial, okay, with parameters k and p, then capital Y, the set of values y can take is 0 to k. Okay, if y is Bernoulli, the set of values y can take happens to be 0 and 1. Okay, if y is geometric, the set of values y can take is 1, 2, 3, or any other natural number. Okay, now this summation, in this summation, y is a dummy variable. Okay, think of every summation like a for loop. Okay, every summation is like a for loop, and this y is just the dummy variable in the for loop. Okay, at the end, when you finish running through the for loop, the dummy variable doesn't matter. Okay, the result at the end has nothing to do with the dummy variable. Okay, so this summation does not depend upon the values of little y. Okay, it just runs through all values. Okay, it the only thing it depends upon is this capital X, the value that capital X can take. Okay, so that's what I meant by saying that the expectation of y given x, it's a function of x, it's not a function of y. Okay, so everyone okay with it? Right, so when, for many of these things, for many times when you see these summations in math, think of how you would do it in programming. Okay, so if you're comfortable with programming, this is what you would do. You would do the summation like a for loop. Okay, and this variable that is there in the sum corresponds to the dummy variable you would take in the for loop. Okay, so when you're the result, so you're doing a summation like this. So the result is, you initialize the result and then you would say for I in y, result equals result plus or y times probability of y equals y given right. So you do something like this. Okay, and then eventually you print result. Right, so this is kind of what you're doing. Okay, what this result is, okay, does not actually depend, I mean, what the result is does not actually depend upon this dummy variable. This dummy variable just goes through all values in this set, and that's the end of it. Okay, it matters what set this is. Okay, but the dummy variable does not play any role. You could replace it with anything else. Okay, the result would still be the same. Right? So in the same way, like this summation is a function, yes, of course, it's a some function of what value x can take. Okay, it's also a function of the set of all values y can take. I mean that, but that has something to do with the random variable itself. Okay, but it is beyond that. It's not a function of y. Okay, it's not a function in particular about the values y can take. Okay, right? So it's not a function of little y in that sense. Okay, so is everyone okay with this? Okay, so here is the story. So we have our huge universe. Right, now in this universe, okay, the random variable x partitions the universe into various, depending on the values it takes. Okay, maybe you have some partition of the universe. Okay, maybe x1, so this is the event x equals little x1. Okay, this is the event x equals little x2. This is x equals little x3. Okay, so now for what is a random variable? A random variable maps every point in the universe to a number. Okay, so that's the definition of a random variable. Now this random variable, the conditional expectation of y given x, okay, so this is what it does. It takes any point here, and every point here is mapped to the number expectation of y x given little x1. Okay, every outcome here is mapped to the number expectation of y given x equals little x5. Okay, and so on. Right, so it maps every number in the event x equals x5 to the same number, that is expectation of y given x equals little x5. Okay, does that help? Okay, it is now very possible that this number and this number may be the same. They may be different, they may be the same. Okay, so but that's okay. Okay, but that is how this expectation of y given x behaves. Okay, it maps every point in the universe to the number expectation of y given x equals little x of omega. So takes a point. So the random variable expectation of y given x takes a point omega in the universe. Okay, if I take a point omega in the universe, okay, x maps this point to x of omega, which is some number. Okay, because x is a random variable, x maps this point to x of omega. Okay, so I'll write something like this. Okay, now expectation of y given x takes that same point, okay, and maps it to the number expectation of y given x equals capital X of omega. Okay, so it is something like this. It takes the partition of the universe that x made, okay, and to each part in this partition, it assigns the number corresponding to expectation of y given x equals the value that x has taken. Okay, so eventually when you look at the partition that expectation of y given x makes, okay, it could correspond to the same partition that x made, except that each part now may be potentially as a different number assigned to it. Okay, or depending on exactly how the expectations pan out, it could do a strictly coarser partition of the universe than that x made. Okay, for example, if expectation of y given x equals little x1 equals the expectation of y given x equals little x5, okay, then both the events x equals x1 and x equals x5 will be mapped to the same number. Okay, so it's a coarser partition in general than what x makes. Okay, sometimes the same partition, sometimes a coarser partition. Okay, is this clear? Right? One way to, a completely equivalent way is to think of expectation of y given x is a function of x. Okay, it's a function of x, right? So just like we write something like this, 2 times yk or yk plus kp, they're all functions of yk. Okay, because if you change the value of yk, you change the estimate too, and that's kind of how you want it. Okay, does this make sense? Okay,
Yeah. Could we see like a numerical example?
okay. Yeah, we are going to do a numerical example, yes. But conceptually, like, is this okay? You're going to help me do a numerical example. Okay, we are going to use small numbers. This is not a it's not a terribly interesting estimation problem. Okay, but to, this is purely like something that we are doing um, just to get the hang of this. Okay, okay, so let us say we have x1 and x2. Okay, they are both Bernoulli P and they are independent. Okay, just two random variables. Okay, they're Bernoulli P random variables and they are independent. Okay, so give me the probabilities of each of these. What's the probability both are 0?
Be like 1 minus p squared.
1 minus p squared, very good. This one? 3 times 1 minus p minus 1 minus p and p squared. Okay. Okay, so we are going to do like a problem that we have already seen, okay, but we are just going to do the computations numerically just so we are happy. Okay, so y1 is going to be x1, okay, y2 is going to be x1 plus x2. Okay, so we want to estimate or like forget this too. Okay, so we want to estimate y2 using x1. Okay, and we'll estimate x1 using y2. Okay, so we'll do both. Okay, so how do we estimate and we are going to use the expectation of y2 given x1. Okay, now what is right, so this is what we are trying to compute. Okay, so I'll just move this to the next page so I can write these. Okay, so we are going to compute this conditional expectation. Okay, so tell me the values of y2 for every point in the universe. There are 4 points in this universe. Tell me the values of y2. When both x1 and x2 are 0, what is y2?
0,
0. Here?
1,
1 and 2.
and 3.
Okay. So let's try to compute what is the expectation of y2 given x1 equals 0. So, right? So let's compute this. Okay, we want to so what is the event x1 equals 0? Just before we do this, let me do this proper. What's the event x1 equals 0?
It'd be like 100%.
No, x1 equals 0. The event x1 equals 0 is 0, 0 and 0, 1, right? So these two outcomes, correct? This is the event that x1 equals 0. Okay, so in this universe, right, like if I also draw it visually, there are 4 points 0, 0, 0, 1, 1, 0 and 1, 1. There are 4 points in this universe. Right, so these 2 points, okay, so x1 partitions the universe like this. Okay, the 2 green points are x1 equals 0. Okay, so the green points correspond to the event x1 equals 0 and the orange points correspond to the event x1 equals 1. Everyone okay with this? Okay, now for every point, so now we are looking at, we are zooming in, okay, on the event x1 equals 0. Okay, now we want to compute expectation of y2 given x1 equals 0. Okay, so for that we first need the conditional distribution. Okay, so we need the conditional distribution of y2 given x1 equals 0. Okay, who can help me with this? Right, so for this, what are the values y2 can take if x1 equals 0?
1 or 0.
Very good. Right, so those are corresponding to this event, right? So this is 0 or 1. Okay, when x1 equals 0, y2 can take on values just 0 or 1. Okay, what's the probability that y2 is, what's the probability y2 is 0 given x1 equals 0? We'll do it very slowly. Tell me from first principles.
Go for the joint probability, right? The probability that y2 equals 0 and x1 equals 0 times the prior, or divided by the prior rather.
This is conditional, right? So this is divided by the probability x1 equals 0. Okay. Okay. So what is the probability y2 is 0 and x1 is 0? Right. So there's just one outcome. Okay. The outcome 0, 0. Okay. There's just one point in the universe that satisfies y2 is 0 and x1 equals 0. Okay. And that corresponds to x1 is 0 and x2 is 0. Okay. So this probability in the numerator is just 1 minus p squared. Okay. What's the in the denominator? What's the probability x1 equals 0? Right. Also 1 minus p. Right, so this probability is just 1 minus p, and the probability y2 equals 1 given x1 equals 0. Now you can do it just, you can just give me the final answer. You'll do it in exactly the same way, but you can just give me the final answer here.
Just be p, right?
It will be p, right? And the conditional expectation of y2 given x1 equals 0 will be 1 minus p times the probability y2. So sorry, this runs over 0. Okay, the value that y2 can take times the probability y2 equals 0 given x1 equals 0 plus 1 times probability y2 equals 1 given x1 equals 0. Okay, so this 0 and this 1 come from here. I just run through all the values y can take, and those values are 0 and 1. So there are only two values that y2 can take, right? And 0 and 1, okay? Well, conditioned on x1 equals 0. Okay, I just run through all the values that y2 can take, okay? And take their weighted average. But when I take the weighted average, I use the conditional distribution of y2 given x1 equals 0. Right? So when x1 equals 0, okay, this is equal to p. Okay, so when you do the computation, the first term goes to 0. The first term is 0, the second term is 1 times p, and that is p. Okay, so this means that when x1 is 0, the conditional expectation of y2 given x1 equals 0 is p. That means that in this picture, the conditional expectation random variable, it assigns to this point the value p, it assigns also to this point the value p. Okay, so here I'm writing a third random variable. This is the conditional expectation of y2 given x1. Okay, so to both these points, I assign the number p. Okay, does that make sense? Okay, and similarly, you can do the computation for expected value of y2 given x1 equals 1. Okay, and you'll find that this is going to be 1 plus p.
Could you Could you explain to me why the coefficient in that first term, the 0 times the probability y2
Right.
equals 0, why that 0?
Oh, because these are the values that y2 can take, right? So the two values that y2 can take are 0 and 1. Okay, when x1 equals 0. So we just run through each of these values. Okay, so we just run through each of these values. Okay, I take the weighted average of all the values that y2 can take when x1 equals 0, but I weight it not by the distribution of y2, but the conditional distribution of y2 given x1 equals 0. Okay.
All right, that makes sense. Thank you.
Okay, so let's do this again then. So let's do this fully. We are going to look at the conditional distribution of y2 given x1 equals 1. Okay, what are the values y2 can take when x1 equals 1? Right, so when x1 equals 1, what are the values that y2 can take?
You take 1 or 2.
1 or 2? Right, so the expectation of y2 given x1 equals 1 will be, I run through each of these values, 1 times, I'm going to weight it with the probability y2 equals 1 given x1 equals 1, okay, plus 2 times probability y2 equals 2 given x1 equals 1. Okay, so what are these values? This is 1 times, what's the probability y2 equals 1 given x1 equals 1? Right, so y2 equals 1 given x1, sorry, apologies. y2 equals 1 given x1 equals 1 corresponds to this outcome. Okay, here y2 is 1 and x1 equals 1, so the joint probability is p times 1 minus p. Okay, but I divide it. So let me do this way. Probability y2 equals 1 and x1 equals 1 divided by the probability x1 equals 1 plus 2 times probability y2 equals 2, x1 equals 1 times the probability x1 equals 1. Right, so and this is 1 times, this probability is p times 1 minus p, okay, and I divide it by p, okay, and here I have p squared divided by p, right, so this is 1 times 1 minus p plus 2 times p, this is 1 plus, okay. Right, so are the computations okay? Right, so here, so what it means is that for these two outcomes, okay, they both correspond to x equals 1, I assign 1 plus p. Okay, so this random variable, the expectation of y2 given x1, okay, it assigns to the outcomes in this following manner. Okay, so what I'll do is I'll just carry this table elsewhere because it's getting a little too congested. Let me just draw it neatly somewhere else. Same table. Let me go. Y is 0, 1, 1 and 2. The expectation of y2 given x1, this random variable, is p, p, 1 plus p and 1 plus p. Can you tell me how the random variable expectation of y2 given x2 will be, just by symmetry? What will it assign?
It'd be identical, right?
No, x2, right. So the computations are almost identical, okay, but not the mapping from points in the universe to the numbers, right? So yes, so here x2 is 0 here and here, okay. So these two outcomes get the value p, okay, and x2 is 1 here and here, so this 2 get 1 plus p. So that's right, Stephen. Right, so this is the expectation of y2 given x2. Okay, so they're both random variables, okay, and they assign to every point in the universe a conditional expectation. Okay, so is everyone clear on this? Okay, so expectation of y2 given x1 and expectation of y2 given x2, they're two different random variables. Okay, actually the set of values they take are identical. They're both p and 1 plus p for two outcomes each. Okay, but their mapping from the outcomes to the values is different. Okay, so they're two different functions. Okay, everyone okay on this? Okay, so let's do this one. What will be the expectation of x1 given y2? Okay, so now this is a function of y2. Okay, so this is like saying I give you the value of y2 and you need to tell me what is the value that x1 can take. Okay, so can you tell me what is the expectation of x1 given y2? Right, so now the values, so okay, so there are three values y2 can take, 0, 1 and 2, and two values that x1 can take. Okay, so help me compute this.
So as before, I think we're going to look at the conditional probability of each situation.
Right, so
So
tell me systematically.
so what did you, it was given y2 equals 1, or just given y2 in general?
Okay, so this is a random variable. So we are going to write this random variable in the final column of this table. We are going to write the values here. Okay, so when we compute when we say expectation of x1 given y2, it's not a number, right? It's a mapping from every point in the universe to numbers. Okay, so it's like saying fill up this table for me, right? So you need to give me all these four values one by one. Right, so remember what we did when we computed expectation of y2 given x1. Okay, we filled up these four values of the table one by one. Okay, and we said, okay, for the first two rows, they both correspond to the event that x1 equals 0, so they'll have the same number. Okay, the last two rows both correspond to the event x1 equals 1, that is the value of x1 is the same, okay, in the last two rows, so they'll correspond to the same number, and then we computed each of these numbers. Okay, so here y2 takes on three different values. Okay, this row corresponds to y2 equals 0. Okay, both of these rows correspond to y2 equals 1. Okay, so they'll get the same number. Okay, and the last row correspond to y2 equals 2, and that will get another number potentially. right? So we need to compute the black number, green number, and the blue number. Okay, so the first one to look at is the expectation of x1. Very good. So Tricia, right? So first one to look at is the expectation of x1 given y2 equals 0. Okay, now x1, so what is this expectation? Now if y2 equals 0, what are the values x1 can take?
0.
Just 0. Okay, and probability x1 equals 0 given y2 equals 0 is, you can say it is either so this is 1 minus p squared divided by 1 minus p squared. Okay, and this is 1. Okay, another way of saying that if y2 is 0, x1 is guaranteed to be 0. Okay, so what is the expectation of x1 given y2 equals 0? This is 0 times the probability x1 equals 0 given y2 equals 0, which is 0 times 1, which is 0. Okay, so this tells us that the black number is 0, which is good because it tells you that if you know y2 equals 0, the only possibility is that both x1 and x2 are 0. Okay, so this better estimate x1 equals 0. Okay, if it estimated anything other than 0, like, we should be terribly suspicious. Okay, because it does tell us the correct value of x1 here, right? So this is good. Okay, what about x1 equals 0? So what about the expectation of x1? Okay, so what do we do next for the I think it was the green number. Yeah, what's the green number? This is the expectation of x1 given y2 equals 1. Right? So what is the expectation of x1 given y2 equals 1? Okay, if y2 equals 1, what are the values x1 can take? 0 or 1. Very good. Right, so we want to compute the expectations of x1 given y2 equals 1 will be 0 times the probability x1 equals 0 given y2 equals 1 plus 1 times probability x1 equals 1. Let me draw these in color. Given y2 equals 1. This will be 0 times probability x1 equals 0, y2 equals 1 divided by probability y2 equals 1 plus 1 times probability x1 equals 1, y2 equals 1, probability y2 equals 1. Okay, now this term is multiplied by 0, no point computing this term. Tell me how to compute this. What's the probability x1 equals 1 and y1 equals 1? What's the probability x1 equals 1 and y2 equals 1?
P times 1 minus P.
Very good. What's the denominator? Probability y2 equals 1.
2 equals 1. Be like
Very
1 plus 2P.
no. So, okay, so this is the event that x1 equals 1 and y2 equals 1. Okay, the event y2 equals 1 are these two rows. Okay, y2 equals, so the probability y2 equals 1 is 2 times p times 1 minus p. Okay, it's also the binomial probability. 2 choose 1 times p times 1 minus p. Okay, so this is 1/2. Okay, so here this random variable will assign to these two numbers 1/2. These two outcomes 1/2. Okay, what is the expectation of x1 given y2 equals 1? Can you do this by inspection without actually having to do computations?
X1 has to be 1 if Y2 is 2.
Right, so this will be
Be 1.
Yeah, so this will be 1. Very good. Okay, so this makes complete sense because when y2 is 0, you know for a fact that x1 has to be 0. Okay, so your estimate of x1 comes out to be 0. Same thing, if y2 is 2, you know for a fact that x1 has to be 1. Okay, so is your expectation, your estimate. Okay, but if y2 equals 1, okay, you know one of x1 and x2 has to be equal to 1. Okay, and conditioned on y2 equals 1. Okay, both of them have equal probability. They both have probability 1/2. Okay, because 0 1 has probability p times 1 minus p, but so does 1 0. Okay, 1 0 and 0 1 both have equal probability, and that's why we get a 1/2 here. Okay, and this will be our estimate of x1 if you see y2. Okay, so does that make sense? Okay, so we'll continue next class. Let me stop recording.